section here, Chapter 11, Section 5, we will be slowly working towards finding the area of underneath a curve. But before we do that, I want to talk a bit about this symbol. This symbol right here is called a summation symbol. And what it means is that we're going to take an expression such as, let's just keep it very basic, such as x, and we want to find the sum of this as x starts at 1, let's say, and goes to 5. So this is where you start your summation, and this is where you end. And so what this would look like is, so this is your whole summation symbol, and it is used to find the area underneath curves. But the way this works is that you substitute 1 in, so it's 1 plus, and then you keep doing the substitution until you get up to 5, just like this. So the result of this, that's 9, 12, 15, the result of this is the answer to what this expression is right here. It's the sum as x goes from 1 to 5 of x. Let's try another one. Here I've got the sum as, it can be any variable. N goes from 1 to 4. Let's say it's of n plus 1 to the second. So what this looks like is you substitute 1 in, 1 plus 1 to the second, plus 2 plus 1 to the second, plus 3 plus 1 to the second, plus 4 plus 1 to the second. So you keep doing this summation until you get your answer. Here's what we've got. We've got 2 squared is 4, 3 squared 9, 4 squared is 16, and 5 squared is 25. So if we add all these together, we get 54. Okay, now, so this is how the summation works, but how we're going to use the summation is we actually will have some formulas, and here are those formulas. We've got the summation as I goes from 1 to n is unknown, of just a constant. We've got the summation of 1 to n of an expression I, where I is n times n plus 1 over 2. We've got the summation of 1 to n of I squared, which is n times n plus 1, 2n plus 1 over 6. So all of these equations actually will find the result of the summation, so we don't have to write it all out in this format right here. Writing it all out in this format obviously takes some time. And so we're going to have these formulas, which the formulas will be available to you when you need them. So just to give you an idea and show you some examples here, this first problem is to evaluate the sum from 1 to 4 of the constant 5. Well, the formula is this. If you look back at your formula, it's this one right here. So it's just the constant right here times the n value. So my constant 5 times n, 4, equals 20. So simply what I'm doing is I'm just substituting into my formula. All right, now here we've got the summation as I goes from 1 to 20. And so now we're looking at this formula, I. So it's n times n plus 1 divided by 2. N times n plus 1 divided by 2. So this would look like 20 times 20 plus 1 divided by 2. This equals 20 times 21 divided by 2. This is a total of 210. And then I to the third here, if you want to look at I to the third, let's go back to the formula. I to the third is this, n squared, n plus 1 squared over 4. N squared, n plus make sure that's squared, n squared, yep. N plus 1 squared all over 4. So when I follow this, here, my 1, as it approaches n, and this n is supposed to be 100 for you guys. So let's put it, so it's 100 squared. 100 plus 1 squared all over 4. So if you evaluate that, we've got 2,500. I just went ahead and divided by 4. 100 squared divided by 4 is 2,500 times 101 squared. Evaluate that and you get 25,502,500. So this is how the summation formulas work. You're going to do some substitutions. Now, along with all of these formulas, we do have ways of simplifying some things that don't quite look like an I squared, I to the third, and so on. So I'm going to show you what we can do with this expression. All right, first of all, with this division of n squared, I can write this summation by factoring out the n squared, so it's 1 over n squared. And then you can see here we've got the summation as I goes from 1 to n of 2i minus 3. Well, there's a rules that we have that allows us to take this 1 over n squared and actually separate the summation. So I can take the summation of the 2i. So it looks like this. I can also, any coefficients can also be written in front of your summation. So 2 times the summation of, as I goes from 1 to n, of I, and then minus, what we've got here is 3 times the summation. And we don't even need to write the 3 in front. We can just write it as the summation as I goes from 1 to n of 3. And so we're able to take all of these parts in the polynomials and separate them into individual summations. So then here's what we will have. So then I went ahead and copied this over to another page, and what we're going to do is try to evaluate this. So this is 1 over n squared. This is just 2 times, and when I multiply here, the formula for the summation of I is n times n plus 1 all over 2. Then minus the summation here would be 3 times n. So I'm just, again, substituting what I know from the list of formulas that are right here. So I just use this one and this one. My last thing that I want to do here is I'm going to go ahead and simplify all of this expression down to something smaller. I've got 1 over n squared. I'm going to leave that alone for a little while. Equal, or not equals, but multiplied by. If I multiply here, the 2's cancel. So this is n squared plus n minus 3n. This is 1 over n squared times n squared minus 2n. And if I distribute here, this is n squared over n minus 2n over n squared. If I keep simplifying this down, it's n squared minus 2n all over n squared. And I can factor an n out from both of those. So I'm working up here. Okay, I'm working towards this direction for some space. So take an n out, you get n minus 2 over n squared. So final answer is n minus 2 over n. And that's it. That's how the summation is going to work and how you can use some of these formulas. As we continue here, in this portion right now, we're going to be finding the limit of a summation. And in order to do that, we generally just apply the summation formulas and their properties, and then we will use the degree techniques to find the limit. And remember, the degree techniques are this. If the degree of the numerator is less than the degree of the denominator, then the limit is 0. If the degree of the numerator is equal to the denominator, then you do the ratios of their coefficients, and if n is greater than the denominator, then the result is no limit. All right, so let's go ahead and put this into action. We've got the first example. It says, find the limit of s of n as n approaches infinity. And so here we've got, which we're supposed to do this summation. Again, when we work the summation, this is our process. I will find the limit, but right now I'm going to work on the summation. I'm going to go ahead and bring the 1 over n to the third out in front. Multiply by the sum as I goes from 1 to n. I'm going to separate the I and the 5 of I minus the summation as I goes from 1 to n of 5. I'm going to work on this before I go to actually identifying the limit. So 1 over n to the third. This right here would be the summation formula is n times n plus 1 all over 2. And then this is what the formula would be 5 times n. So there I've evaluated the summation. And I'm going to go ahead and simplify all of this down as far as I can. At this point in time, I'm ready to distribute. If I distribute my 1 over n to the third, this becomes n times n plus 1 over 2n to the third minus 5n over n to the third. If I put all this together here, what I would want to do is I'd want to find a common denominator. Okay, my common denominator between these two, what I would need to do is multiply my second fraction here by 2. And then with this common denominator, I'm going to now go ahead and write it as one fraction. So this is n times n plus 1 minus 10n over 2n to the third. Keep simplifying this. This is n squared plus n minus 10n over 2n to the third, which is n squared minus 9n. I think that it looks as though we've got minus 9n there over 2n to the third. Now, when we take the limit as n approaches infinity of this expression, we can compare the degree. The degree on top is 2, the degree on bottom is 3. That indicates it's less than, so the result of the limit is 0. Final answer. All right, in this next problem again, trying to find the limit, I'm going to go ahead and write some of these expressions so that we can evaluate the limit. Problem here, with this expression being squared, I'm actually going to take and FOIL this and then distribute the 1 over n before doing anything with the limit. If I square this expression, 2 plus I over n times 2 plus I over n, it equals 4 plus 2in plus 2in over n, and then plus I squared over n squared. Now if I multiply all of that by 1 over n, the result is this. We've got 4 over n plus 2i over n squared, and really here I've got 2i plus 2i, so let's go ahead and add those together while we do this. That's 4, so this was plus, that's 4 I over n and then squared, and then it's plus I squared over n to the third. All right, by it being able to put all of these together as one fraction, the common denominator would be an n to the third. So this would be 4n squared over n to the third plus, here I've got 4n I times n to the third, or over n to the third, and then plus I squared. So all of this is replacing this summation. Okay, so I'm going to go ahead and copy this over here with all my symbols. That's what I have. Now with the way the summation again works is that you can always pull constants and coefficients out in front of. And so I'm going to work on the summation right now, but I have 1 over n to the third times the summation of I goes from 1 to n of 4n squared, and then plus the summation I goes from 1 to n of 4ni, and then plus the summation as I goes from 1 to n of I squared. All right, I'm going to go ahead and continue to simplify this. So this is 1 over n to the third. I can pull my n squared in front of this, n squared times the summation of that I goes from 1 to n of 4. We're going to work on that in a second. I can pull the n in front of this one. So that would be of, I can pull the 4 with it. So that's just going to be of I. Come back and rewrite that. I'm pulling the 4 and the n with the coefficient here. And then plus, I can just leave this as the summation that I goes from 1 to n of I squared. Now I'm going to go ahead and eliminate my summations. So this is 1 over n to the third times n squared times, and then 4 here with the summation would be 4n, plus 4n times, and the equation for I is n times n plus 1 over 2, and plus, and the equation for your I squared is n times n plus 1 times n plus 1, or 2n plus 1, n times n plus 1 times 2n plus 1, all over 6. All right, here we go. So we've got all of our summation symbols eliminated, and before I can take the limit of all of this, I need to have all of my variables combined and figure out the degree. All right, let's simplify some of this. I'm going to have to go, transfer over to another page, but 1 over n to the third. N squared times 4n is 4n to the third. Plus, if I distribute my n times n plus 1, it would be n squared plus n times 4, so it's 4n to the third. So I'm going to distribute that. That's n squared plus n. So 4n times n squared, and then 4n times n would be plus 4n squared. That's all over 2. I'll work on this simplifying in a second. Plus, if I FOIL all this, I get 2n squared plus 3n in the middle plus 1, multiply that by n, and it is 2n to the third plus 3n squared plus n. This is all over 6. My next step is going to want to try to, simplify some of this. I'm going to distribute this n to the third, find a common denominator, and go from there. Okay? All right, so let's go ahead and distribute this n to the third, 1 over the n to the third. That would be 4n to the third over n to the third. Again, I'm leaving this alone for temporarily. So 4n to the third over n to the third. And then here I'm going to cancel this 2 here with both of those 4s, so they're 2's. So it's 2n to the third over n to the third. And then I've got, again, another 2. But this is 2n squared over n to the third. And then I'm going to distribute the 1 over n to the third to the last expression. So 2n to the third plus 3n squared plus n. And this would be over 6n to the third. So I just distributed again. Last step here that I'm showing you is I'm distributing the 1 over n to the third to each of these expressions. And now let's see if we can go ahead and write one denominator. So let's combine some of my like terms here. This would be 4 plus 2. That's 6n to the third. Plus 2n squared plus 2n to the third plus 3n squared plus n. This is over 6n to the third, and each one of these are over n to the third. In order for us to have a common denominator, we need to multiply all of these by 6. So this 6 over 6, 6 over 6, and this would give us 36n to the third plus 12n to the second plus 2n to the third plus 3n second plus n all over 6n to the third. Last step would be to finalize all common parts. My common parts here are, I've got 36n to the third plus 2n to the third. And 36n to the third plus 2n to the third is 38n to the third plus 15n squared plus n all over 6n to the third. All right, we're still not done because, again, what we are supposed to do was take the limit as n approaches infinity of this whole expression. Well, the degrees are equal, so we do the ratio of 38 to 6 reduced down, that is 19 thirds. So the answer to this is 19 thirds. All right, this is going to conclude all of the summation work that we have, and here's your assignment.